So, welcome to our discussion on hydrodynamic interaction. In the last lecture, we looked at interaction between two spheres, considering that the two spheres are separated by a distance which is significantly larger than, I think we used r, significantly larger than the radius of the spheres. And we were able to do this by getting introduced to a method known as a method of reflections. So, the primary idea is that when you are considering this motion, you have two spheres and we were looking at a problem of sedimentation. So, sphere 1 was settling under the action of an external force. If it is sedimentation, then that is its own weight. Same applies for sphere 2, which was also settling under the action of its own weight. Now, if there was no interaction, each of these spheres would fall with their respective Stokes terminal velocity. That is something which is obvious. You do not have anything else in the problem. They are falling in a quiescent medium. So, they would just fall with a terminal velocity. So, the question was that if they are not so far apart, then how would their motion change? And to analyze this, obviously, if you want to do this in an exact manner, you would actually have to solve this entire problem numerically. And you have to solve a problem where there are these two no slip, no penetration boundary conditions, and then you also need to ensure that when you are solving this problem, you solve for the flow field such that at every instant of time, when if you are doing this numerically, the force acting on each of these objects should be held fixed. So, instead what we went about doing is, we said if you imagine for the time being just the sphere 1 in isolation, which is where sphere 1 is settling under the action of gravity, and because it is a problem of sedimentation, we can go back to what we have learned from our translation problem, and we can say that the disturbance velocity that is created by this particular sphere is given by the combination of a Stokeslet and a potential dipole. This is again things which we have already done in quite some detail. Sphere 2 is now present in a flow field that is generated by sphere 1, and so we said the motion of sphere 2 cannot be its own terminal velocity, but rather it would be due to the ambient velocity that is due to sphere 1's disturbance field or sphere 1's velocity field. So, there is an external flow u infinity, which is now the flow field that is generated by the translating particle, which is sphere 1. So, we go back and use Faxon, and by using Faxon we are able to actually find that sphere 2 does not fall with its ambient settling velocity or the terminal the isolated terminal velocity, but there is a correction. And because we are doing all of this in the far field, the correction we can just consider the leading order Stokeslet part. So, we are ignoring the part which is the Laplacian from the Faxon, and even in the part which is due to the disturbance velocity field evaluated at sphere 2, we are just looking at the Stokeslet part. So, this actually gives us the first calculation of interaction between two spheres. You are saying sphere 1 falls due to gravity, sphere 2 falls due to gravity. The motion of sphere 1 creates a velocity field which is influencing sphere 2, and if they are sufficiently far apart, sphere 1 for the purpose of sphere 2 can be modeled as a Stokeslet, and sphere 2 for the purpose of sphere 1 can also be modeled as a Stokeslet. That is the idea of what we have done as the first level calculation. And after doing all of that, we arrived at an equation that the relative velocity between the two spheres can be expressed in terms of the force acting on the two spheres and obviously their size, which if the spheres are equal leads to them translating with the same velocity. They are translating with the same velocity, but that is not necessarily equal to the Stokes terminal velocity. It will not be. They are going to move with the same velocity, but that velocity field is not the Stokes terminal velocity. That is an important point. This is going to be Stokes terminal velocity only when you are infinitely far apart. So, when you then move on and try to write down what is the average velocity, in this case because they are equal in size, the average velocity is also equal to the individual sphere velocity. The average velocity is enhanced from the terminal velocity. So, you obtain in the end that there is a terminal velocity which is increased by a factor of 1 plus 3a by r if the two spheres were settling in an orientation, that is where the line joining the center is perpendicular to gravity, and if it was parallel, then u parallel by u isolated or Stokes is 1 plus 3a by 2r. So, that was basically the conclusion. So, there are multiple things you can do now with this method of reflection. I am not going to elaborate more on this, but few points I want to just make here. This approach of method of reflections that we have done is a method of reflections done for a mobility problem. The reason I am saying this is a mobility problem because the force acting on the spheres are fixed. Now, you can do the same exercise just apply the same approach for a resistance problem. So, what would be a resistance problem? A resistance problem is you have two spheres which are not under the action of a constant force, but rather they are moving with a constant velocity. I mean, you can also include angular velocity if you want, but what is fixed in this approach is the dynamics of the particle. So, what you need to compute would be the forces acting on the particle. So, as I gave an example of this is that of a fixed bed. A fixed bed is where you can think of there are an array of particles placed in some order, and you have decided that these particles are immobile, they are not moving, which means u1 equal to u2 equal to 0, and you are trying to find out what is the force acting on individual particles, the drag force on individual particle. So, what I will leave as an exercise, because you can take this and do this also for the resistance problem, I want you to think and justify the statement I will make right now, which is the hydrodynamic interaction due to the resistance problem using the same method of reflections is more severe or is stronger than that from the mobility problem. And the way you can think about this is you can think of a picture of this particular kind, where if you say the object is under the action of a constant force or the object is translating with a constant velocity, at the leading order you know it is going to create a velocity field which would be a Stokeslet plus a potential dipole. Then the sphere 2, it is either required to move with a constant force or it is going to move with a constant velocity. If it is going to move with a constant force, let us say the constant force is force free, then you would have a certain kind of an interaction. Whereas, if you say that it has to move with a constant velocity, which is the resistance problem, then there would be a certain. So, you are basically asking the question, what would be the disturbance created by sphere 2 by being present in the velocity field of sphere 1. So, if it is a resistance problem, it will create one kind of a velocity field, while if it is a mobility problem, sphere 2 will create another kind of velocity field. So, it is at that level you will actually start to think about which one should be stronger, and the claim I am making here that interactions are going to be stronger in a resistance problem than a mobility problem. Okay. So, this requires just a little bit of work with the reflections, and all you have to do is consider these two problems. So, in each of these cases, the disturbance that it creates obviously has a order 1 over r plus order 1 over r cube. The question is, what would be the response of sphere 2 in both the cases? Would it generate the same disturbance field, or would it generate a different disturbance field? In the calculation we did in class, we did not go to the next reflection, right. So, this is something which I will leave you at it, and today's lecture is still going to be on the interaction part, but we are going to rather focus on the opposite of limit. So, this is now hydrodynamic interactions when particles are close to each other. So, we studied the previous problem using method of reflections by saying that they are far apart, and then I can basically go about finding out their motion, finding out their behavior by looking at the leading order Stokes-led velocity field. This approach is what is formally known as a lubrication calculation, where I have two spheres, and in the discussion today I am going to consider the two spheres to be identical in size and shape, and I will also consider them to be spherical. But nothing that I am going to say here is specific to equal size spheres. They can be taken to spheres which are of different sizes, and in some scenarios can also be taken for particles that are not necessarily spherical. But primarily the focus of what we are going to discuss is going to be in the context of two equal size spherical particles, because we have seen from the previous discussion that whatever we did in that reflection based calculation is obviously going to work when the particles are far apart. Once I bring the particles closer, as we said, we need more and more terms in the reflection calculation. So, when you bring them close together, when these two spheres are close to each other, you can have two kinds of relative motion. There can be a motion where the spheres are approaching towards each other along the line joining the center, or the spheres are moving relative to each other normal to the line joining the center. So, this behavior is known as a squeeze flow or the squeezing motion, whereas this behavior is a shear flow or a shearing motion. So, when you are trying to squeeze the fluid here, so you have two surfaces, you are trying to push them towards each other, and without any loss of generality we are going to assume that one of the sphere is held stationary and the other is moving. So, you are looking at relative motion. So, when you are trying to make the spheres move towards each other along the line joining the center, you are trying to drive out the fluid between the gap, right. You are bringing the two surfaces close together, you are trying to push the fluid outside. So, here you are squeezing out the flow. There is a fluid which is getting squeezed out. Whereas in this case, when you are trying to make it move perpendicular to the line joining the center, the flow is a top surface that is moving and a bottom surface that is held fixed. So, it is like a shear flow. I am just drawing things locally and we will expand upon it a little bit. So, again here I am just going to primarily go through what is going to happen for squeezing motion. It is easier to explain and it is a classical problem of what would be the force acting on these spheres if they were having a relative velocity towards each other with a velocity W naught. I will touch upon a little bit of the shearing motion towards the end, but that requires a more detailed calculation. So, if you fundamentally understand how this calculation is done for the squeezing flow, doing it for the shearing motion requires it to be done in a more detailed manner, but the principle remains the same. And the guiding principle for doing this is there is a gap here H naught. We are assuming that H naught divided by A is very small. That is the premise of when I say close to each other, because you cannot just use words like they are close. You have to be a little bit more precise mathematically. So, the precise statement is that there is a small parameter which is defined as H naught by A, that is asymptotically small. Now, H naught, as you obviously can see, is if the center to center distance is given as r, or rather let us say yeah. So, if I define the gap in a spherical coordinate system, I will put r star here is the center to center distance, r star minus 2a. I am considering them to be equal. If they aren't equal, then it becomes r star minus a1 minus a2. That is the smallest gap between the two spheres. Now, what we will do is we will zoom in close to the gap. We are not really going to look into the region far away from the gap, and we will come back to it later that what is the consequence of doing this. Right now, let us just focus close to the gap. And close to the gap, I will design a local cylindrical coordinate system that is sitting on the lower sphere. So, this is sphere 1, this is sphere 2. Sphere 2 is moving with a velocity W naught. So, this is a cylindrical coordinate system. You have two spheres. Imagine that on the bottom sphere you draw a tangent and there is a radial coordinate which is equal to x square plus y square, right, and then z is the vertical coordinate going away from that surface. Now, this surface I will call as z2 of r, it is a function of r, right, and this is z1 of r. Now, what is, let us take sphere 2. What is the equation for sphere 2, the surface of sphere 2? It will be x square plus y square plus z minus h naught minus a whole square is equal to a square, right. That is the equation of sphere 2. The surface of sphere 2 is given by this, right. Now, x square plus y square in the cylindrical coordinate system is r square. So, I can take that a square outside, this becomes, on this it is z2. So, z2 by a minus h naught by a minus 1 whole square is equal to a square. So, this becomes r square by a square plus z2 by a minus epsilon minus 1 whole square is equal to 1. H naught by A is epsilon. Now, we are interested in a region that is close to that minimum gap, right, which means even the value of Z2, the local Z coordinate of that surface that we have, Z2 by A is also going to be small. We are interested in the region. So, what I have done here, I am only focusing on this particular region. So, very close to the gap, the Z coordinate of that surface is much smaller than the radius of the sphere, correct. So, what I will do here, that this square I can open it up and write it as 1 plus 2 epsilon minus 2 Z2 by A. I have removed all the quadratic terms. I am ignoring the quadratic terms by saying that they are smaller. So, I will just keep the terms which are order epsilon. So, Z2 by A is also comparable to that. So, then this is R square by A square plus this is approximately 1. So, I have Z2 is equal to A by 2 R square by A square plus 2 epsilon. Again, this is approximately. So, Z2 is approximately A by 2 into 2 epsilon is H naught, right. You have to remember what is the definition, H naught is equal to A epsilon. So, this becomes R square by 2A plus H naught or H naught into 1 plus R square by 2A H naught. What is this an equation of? Z going quadratically with our paraboloid. So, what you have done is very close to the gap, you have a sphere very close to the gap. When I have considered this cylindrical coordinate system, I have approximated that surface as a paraboloid. So, now if I want to write down what is the gap, so let us say H of R is Z2 of R minus Z1 of R, the local gap anywhere. The local gap is H naught 1 plus, or again it is an approximation, R square by 2A H naught. What is the equation for Z1? If this was Z2, do I need to go ahead and do again Z1? Z1 will be approximately minus R square by 2A, right. The coordinate system origin sits on the sphere 1. So, this particular surface is going to be minus R square by 2A. Okay. So, there is a minus minus plus R square by 2A, which I can then write as H naught 1 plus R square by A H naught. If it was not equal, this would have become R square by H naught into 1 by A1 plus 1 by A2 will become the harmonic mean of the two radius. So, the gap between the two spheres is approximated by this parabola. So, now if I want the curvature term to actually be as important as the first term. So, finally what I am trying to say here is that A H naught, what is it in terms of epsilon? This is A square epsilon, right. So, if I want this term to be order 1, I want that curvature term to be as large as this particular term here when I am trying to approximate. What should be my scale in the radial direction? In the vertical direction, I have H naught is equal to A epsilon. My question is, what should be the length scale in the radial direction? If I say that, if I assume that the length scale in the radial direction is the same as the length scale in the vertical direction, which is A epsilon, then that H of R equation, you will have R square. So, there is a 1 there and then there is a R square, which will go as A square epsilon square, and the denominator will go as A square epsilon, which means the curvature term will never be important in the gap. If you say that this gap when compared to the sphere radius is epsilon times smaller, what should be the length scale in this radial direction, the scale in that direction? If I assume that the scale in the radial direction is identical to the scale in the vertical direction, the conclusion is that this paraboloid becomes a flat surface. So, if I want the curvature, the radial scale cannot be epsilon, but rather it should be R naught square should be equal to A H naught. It is only then that this particular curvature term, see this is the curvature term, right. I want that curvature term in my, after I scale the problem, I want that curvature term. So, if I want that curvature term, I cannot be choosing the same scale in the radial direction as I choose in the vertical direction or normal direction. Otherwise, it is going to model the surface, instead of a curved surface, it is going to model the surface as a flat surface. So, if you do that, then your R naught is A root over epsilon. So, the radial scale is larger than the vertical scale. See, the vertical scale is A epsilon, the radial scale is A root epsilon. So, this is coming from geometric considerations. You have taken two curved surfaces and you are trying to basically ask the question that it is crucial for me to realize that this surface has some curvature. This is not two flat plates. So, if I want the curvature, because finally you have to understand that this problem, when I was viewing in the far field, there was a length scale which was A. Everything was scaled by A, but A is not relevant when I am looking at that small gap. The physics of the small gap is determined by a length scale which is much smaller than A. So, I have to rescale my problem. I have to go back to my problem and look at a different way by which I non-dimensionalize things. So, if I say I am going to use the vertical scale as my length scale for non-dimensionalization and go forward and also apply it as a length scale in the radial direction, then the surface, which is actually a curved surface, becomes a flat surface. I do not want that. I want the physics to include the curvature at leading order. That is the basic. See, once you get these ideas clear, then the subsequent part, again as I have said in other context also, is a lot of algebra, but you will not be able to proceed with the algebra if you are not convinced about the argument. Why should the radial scale be, if I say the vertical scale is epsilon a and radial scale is square root epsilon a, it appears very arbitrary. It does not seem like there is any reason to do it that way. What is the justification for choosing that? So, the justification is coming from considerations that the surface is a curved surface, and on rescaling, on choosing this rescaling, I should be able to maintain that curvature at leading order. Then comes the aspect of the flow, because so far we were only discussing about geometry. So, what we have done here, we have approximated the spherical surface as a local paraboloid, and then we have used the argument that because the gap is epsilon times smaller than the radius of the sphere, so that is basically the length scale in the gap direction or the normal direction. On the radial direction, it should turn out to be a square root epsilon. So, now the question is, what should be the velocity scale in the radial and axial direction or the normal direction? Now, the axial direction or the normal direction, the velocity is already set, that is the velocity with which the sphere 1 is approaching sphere 2. I am trying to push sphere 1 towards sphere 2. So, the velocity scale in the axial direction or z direction is W naught. So, now the question is, should U naught, which is the velocity scale in the radial direction, be also the same? How do I find that out? Should I have the same scale? If W naught is the scale of velocity in the axial direction, axis basically means the axis of symmetry joining the two spheres. What should be the velocity scale for the fluid that is moving in a direction perpendicular to the axis or the radial direction? Should it be same, should it be different, or how do we find that out even? So, have you done an exercise like this in the past in any other problem? We are going to use mass conservation. Yeah, mass conservation, and a place where you might have seen this, where you knew length scales and you worked out relation between velocity scale, was in boundary layers. So, you use mass conservation. Mass conservation tells us, if I use the cylindrical coordinate system, even though we do not really need the full detailed form, but if UR is the component in the radial direction, UZ is the component in the axial direction, and I am assuming here that because of the geometry, the nature of the problem is axisymmetric. There is no theta component or azimuthal component, right. So, this is in terms of scales U naught by R naught, right. This one is W naught by H naught, which tells me that U naught should be R naught by H naught into W naught. Now, what is R naught by H naught? R naught is A square root epsilon, H naught is A epsilon times W naught. So, U naught is inverse square root of epsilon times W naught. So, it is much larger than W naught. This is essentially what we do also in boundary layer theory, right. In boundary layer theory, it comes out in a different way. In boundary layer theory, we know that difference in the length scales, and we say that the tangential velocity, if it is U, then the vertical velocity should be smaller than the tangential velocity based on the length scale scaling. Again, the same principle, that mass conservation should be satisfied. if I were to say that the velocity scale in the radial and axial direction was the same, they were the same scales, I would have arrived at a conclusion that I will not be able to satisfy mass conservation, or I will get a trivial answer that the velocity remains independent of the coordinate, a constant velocity, something of that sort. So, to satisfy incompressibility, that if I am trying to squeeze in the fluid along the axial direction, I am basically resulting in a divergence, or in this case a convergence, and the fluid is converging in the axial direction. So, the rate of convergence in the axial direction is balanced by the rate of divergence in the radial direction, which means the velocity with which it actually spreads out should be much larger than the velocity scale with which it comes in. So, now we primarily have almost everything in place to move forward. We have worked out the scale. So, effectively now it is a question of going to our momentum equation and seeing what is going on. So, in the gap, in this gap that I have here, in this gap I am going to write down my Stokes equation. So, the Stokes equation will have a radial component 0 minus dou p dou r plus mu dou square u r dou z square 1 by r. These are again terms which come because of the cylindrical nature of the problem, but as you will see very soon, it's the precise form will not really be so important. Now, let us try to find scales. The pressure scale at this point is an unknown. So, I will say it is P naught. So, this is P naught by R naught. This one is mu u naught by h naught square, right. This term is mu u naught by R naught square, and this is also applicable for the third term. These are scales for each term, that what would be the typical scale of these components in your viscous force per unit volume. Now, between these two terms, which one is going to be larger? The one mu u naught by h naught square or mu u naught by r naught square? This one, right? Because the ratio of the two terms is actually r naught square by h naught square, and r naught square by h naught square is epsilon, radial gradient. This is again reminiscent of what you do in boundary layer theory. In boundary layer theory, when you are writing down your equation, the vertical gradients of the streamwise momentum equation survive over the streamwise gradients of the streamwise velocity or streamwise momentum. It is very similar in terms of what we are doing here. So, it becomes a balance between these two terms. Now, what should be the pressure scale? Pressure scale should be such that the radial pressure gradient should balance the viscous term. You have to imagine what is going on here. You are trying to push the two surfaces. As you are pushing the two surfaces, there is a flow that spreads out. So, that flow that is spreading out is basically due to whatever the pressure gradient that you are creating in the radial direction. Okay. So, this gives me a pressure scale which is mu u naught r naught by h naught square. If I write everything in terms of W and A, this is mu epsilon to the power minus half W naught. What is R naught in terms of A? Right? What is H naught in terms of A? So, this becomes A square epsilon square, right. So, what do you get here as your pressure scaling here? Mu W naught by A divided by epsilon square, right. This is an important result here. The scale of pressure, I mean we will work out what that exact. So, now what is left here is to find whatever is the non-dimensional term multiplying or whatever is the additional non-dimensional function that we need to calculate here. We have found the scale of pressure. What is the scale of the viscous gradient? Mu dou u r dou z. What is the scale of this quantity? Order mu u naught by h naught, right. If I write everything in terms of W naught, this becomes minus half W naught, H is A epsilon. So, the viscous stress is mu W naught by A epsilon to the power 3/2. So, what have you seen from this scaling exercise? The pressure scale is mu W naught by A divided by epsilon square. The viscous stress, this is a viscous stress, right. The viscous stress is mu W naught by A divided by epsilon to the power 3/2. So, as epsilon goes to 0, in the total stress, what is contributing? Pressure. So, as the gap becomes smaller and smaller, the dominant contribution is going to come from pressure. This is an important point here, because we are going to later, when we will calculate the total force, it is sufficient to only focus on the pressure contribution. In contrast, when you do the problem far away, the contribution to force is of the same order between pressure and the viscous stress. When you have calculated the drag 6 pi mu, you would have found there is a partitioning of 2/3 and 1/3 between the two components, viscous stress and pressure. When you are doing this now in the gap, you realize that the predominant force that a single sphere is going to experience is going to come from the pressure contribution. So, even before you do a very detailed calculation, it is important to work out with these scales in order to understand what is it that you will expect. Because now with this scale of pressure, now that you are convinced hopefully that pressure dominates over the viscous stress, the contribution of force is going to come from pressure. So, if the contribution of force comes from pressure, what you need to do here, you need to integrate the pressure force over that small patch. What is the area of the patch? I do not want an exact answer, I want a scale. So, see, if you have to compute area, obviously the area is going to depend on the radius, right. So, it will basically have an A square, that will be the surface area, and there will be an epsilon because you are looking at that small cap of that sphere, right, because that is how you know Z scales, right. The scaling of Z that you have worked out, it is basically will come from. So, there will be an A square epsilon. So, the surface area will be or will scale as A square epsilon, which means the force is going to have a P naught S, which will be mu W naught by A into 1 by epsilon square into A square epsilon, which means the force acting on one of the spheres would be the Stokes drag scaling mu velocity area into 1 by epsilon. This is the key result. Again, we are going to find what that prefactor is. We will work that out, but you should be convinced about this way of arriving at this scaling, that as you are trying to bring two surfaces close to each other, the pressure force or the pressure that is acting on the surfaces is going to far exceed the viscous stress contribution, and this pressure is going to eventually be responsible for the surfaces to experience a force that diverges as epsilon goes to 0. So, if I am trying to push one surface towards another with a constant velocity, if W naught was held fixed and I am trying to find the force, which is the resistance calculation, the resistance to normal motion is going to become infinitely large as the gap gets smaller and smaller. Similarly, if I were to actually pull the two surfaces away, I am basically going to experience a negative pressure in that case, a suction. So, I do not know how many of you have seen this, but if you have two plates which are recently washed and stacked on top of each other, if you have to separate them, there is a lot of force that you need to apply in order to take them apart. So, there is a strong force that is required in order, because you are trying to encounter this large negative pressure that is there. So, now let us try to work out what this is going to be. So, we wrote down the radial momentum equation. So, the radial momentum balance gives us an equation which is zero is minus dou p dou r plus mu dou square u r dou z square. Now, just like the radial momentum equation, you will also have an axial momentum balance, right. So, the z component is 0 minus dou p dou z plus mu 1 by r dou r r dou u z dou r plus dou square u z dou z square. Again, we are not writing down the azimuthal component because we are looking at an axisymmetric problem here. So, what is the scale for the pressure gradient here? P naught by H naught. What is the scale for the radial diffusion of the axial momentum? Mu W naught by R naught square, and this term is mu W naught by H naught square. Is everyone with me with this? Now, let us go back to the variables that we are aware of, which is W naught and A. So, what is P naught? What is the scale for P naught? Mu W naught by A by epsilon square, right. So, this is mu W naught by A, sorry, yeah, into epsilon to the power minus 2, right. That is the pressure scale. Z is H naught is A epsilon. This is mu W naught, R naught square is, R naught is A square root epsilon. So, this becomes A square epsilon, and this is mu W naught A square epsilon square. So, this term is order 1 over epsilon square, this term is order 1 over epsilon, and what is this term? So, what survives? Which means the axial momentum balance is at leading order dou p dou z equal to 0, and should again remind you of boundary layer theory, that the plate normal or the direct momentum balance in the direction normal to the boundary layer basically gives you pressure remaining constant. So, which is to say that pressure is purely a function of radial coordinate, it is not a function of the axial coordinate, right. So, at any point in R, the pressure variation, you can say it has a balance that is coming from a hydrostatic kind of a balance. There is no weight here, but you just have dou p dou z equal to 0. So, you look at this, this is the side view, you look at from the top view at any radius R, if you were to find the pressure would be the same at any point in Z. That is what your lubrication scaling tells you. Now, this makes it particularly easy, because now dou p dou r is independent of Z, right. So, in that equation becomes dou square u z dou z square is equal to 1 by mu dp dr. Sorry, this should be r square, u r u z, sorry, u r, yeah, u r u z. Now, if you integrate this equation, you will have a solution that is u r is equal to some constant, right, the homogeneous solution plus A2 of z plus z square by 2 mu dp dr. What are the boundary conditions? What is the boundary condition in this problem? There are these two curved surfaces, right? The fluid velocity on these curved surfaces, what is the boundary condition? Are they completely immobile, the two boundaries? So, what is the boundary condition? So, u at z equals z2, does it have any radial component? In this cylindrical coordinates, does it have any radial component? None. It obviously does not have any azimuthal component. This is r cap, this is theta cap, but it has w naught. And here 0, 0, 0, because I am choosing a reference frame where the bottom sphere is sphere 1 is held stationary, sphere 2 is moving. So, in the cylindrical coordinate system, the top surface is only moving along the z direction. Okay. So, the radial component should be 0. So, which means u r should be 0 at z equals z1 and z equals z2, and you have to keep in mind that z1 and z2 are itself functions of r. So, u r of r comma z is 1 by mu dp dr. I am writing it as an ordinary derivative because p is only a function of r, z minus z1 of r, z minus z2 of r. Does this velocity field remind you of something? This velocity field appears like a local channel flow or a Poisson flow, right. So, what you are seeing is that if I were to look at a particular radial location, at that radial location I am basically going to observe a local pressure driven Poisson flow. But the Poisson flow is not the same at every radial location, because you have dp dr which could be a function of r, we also have z1 and z2 of r which are functions of r. So, this is not your usual channel flow where we say the flow is fully developed, which means that along the flow direction the channel flow is not changing. So, here if you were to construct this channel flow at different radial location, you would get different maximum velocities, but it is going to be the same parabolic velocity profile. Now, how do I find dp dr? Because what is my end goal? My end goal is to find the variation of pressure and then compute the force. All of this is to basically in the end find a number here. It appears like a lot of work, but it also teaches you how you go about doing this calculation. Scaling argument already gave us that the force is mu w naught a into 1 by epsilon. So, everything that we are doing right now is just to get a numerical factor. Yeah.